In late 2020, physicists in China generated controversy by claiming quantum advantage with a photonic system that's technically not programmable. Other companies have been experimenting with photonic systems, including QuiX Quantum. How do these machines work? Should scientists redefine what quantum advantage means? Join us for a light exploration of light-based quantum computing in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is the CTO of QuiX Quantum, Dr. Jelmer Renema. Welcome to the show. Thank you. Yeah, and it's fun. Right now I'm in San Diego at the IQT conference while I'm recording this, and it's pretty wild. I'm reaching to you all the way in the Netherlands, right?
Yes. I'm coming to you today from actually my home office in the Netherlands.
Excellent. And tell us a little bit about your background in quantum photonics.
You mean my personal background or that of the company?
Yeah, your personal. Yep.
Okay, so I did a PhD in Leiden in the group of Martin van Exter and Dirk Bouwmeester on superconducting single photon detectors. I then did a postdoc in Oxford in the group of Ian Walmsley, then moved back to the Netherlands on a fellowship and started there initially as an academic, and then founded QuiX Quantum in 2019 together with Hans van der Vleckert.
Yeah, so it seemed like your background helped direct the direction of the company, basically.
Yes, absolutely.
Yeah, with that focus on photonics. So QuiX Quantum's relatively young. It's a startup, right? So I guess it's like 3 years old now. So tell us a little bit about the company and why you started it.
So QuiX Quantum was founded based on a piece of scientific serendipity. So what happened was more or less the following. When I was in Oxford as a postdoc, we were looking for devices to do these kind of quantum optical experiments with. And it just so happened that one of our hires in the group was someone from the University of Twente in the Netherlands who said, hey, I know how to get our hands on these devices because there is a group there that is really good at integrated optics and that is working with these things. So we organized that we could actually borrow one of these devices from the University of Twente, take it to Oxford and measure it. And when we did that, we realized that we really had something, let's say. So when I came back to the Netherlands about a year later, I, found the people who had actually fabricated this device. And I said, okay, we really have to start exploiting this technology of silicon nitride optical waveguides. We have to start exploiting this for quantum technologies. And so after some discussions, which took about another half year, we ended up founding QuiX Quantum in January 2019. The company, as this goes, was initially very small, started with a handful of people. In the summer of 2020, so about a year later, we secured a seed round with a few investors. Actually, the last hand that I shook before the pandemic was of the person who would ended up becoming the lead investor. So that was kind of an interesting way to go into lockdown.
Yeah.
And literally we were having, the last in-person meeting that I had was this kind of meeting. So that was kind of an interesting way to go into the pandemic. But anyway, so we had that over the summer. Over the summer of 2020, we had that seed round, and we then grew. So we're now at about a dozen people, and then we also have recently realized hardware sales, right? So we're actually, something that I'm very proud of is that QuiX Quantum, as a lot of what quantum computing is, of course, about selling a promise of the future, but something that QuiX is actually doing where I would say it's ahead of the pack is that it's actually already generating hardware sales, right? So we've sold about half a dozen devices, half a dozen of these quantum photonic processors to both academics and to other quantum startups worldwide. And this is also, why I say we are the market leader in photonic quantum computing hardware, because there are not very many companies that can say that they have sold, half a dozen quantum processor units.
Okay, and your first processor came out really quickly, right? It came out like within a year of the company founding, and I've heard it called record-breaking. Can you elaborate on what like led to that, moniker for that first processor?
Well, so first, I want to say something about why we were able to move so fast. So we at QuiX are organized as a fabless company. So we try to outsource as much of the fabrication as we can. And what we actually did was we took on board the fabrication capabilities of the company that had originally designed this processor that went to Oxford, so the one that was done as an academic collaboration, and we simply iterated further on that technology. And so a lot of what we needed to do to be successful was already there, particularly in the kind of low-level components that we needed. So a lot of the, let's say, groundwork that you need in order to make a good quantum photonic processor is to have low optical loss optical waveguides, right? So our information carriers in our system are photons, and these photons, they want to move at the speed of light. So you need to provide some channels for them to move over, and these channels are what are called waveguides. And the thing that you don't want to happen is that these photons are lost to your computation as they move over these waveguides. And so the thing that actually made us realize that, someone should really get started on building quantum photonic processors out of silicon nitride is when we computed the component density that you can achieve in silicon nitride quantum photonic processors. So it turns out that it's not so much about the optical losses per centimeter that you can specify. So if you talk to an integrated optics person, they will say, I can make waveguides and they have losses of, so and so many decibels per centimeter. It actually turns out that that's not the important number. The important number is losses per component. So one of the reasons why silicon nitride is really good is because it sits at the sweet spot where you can both build relatively compact components, but still have relatively low loss. And so there are other materials out there that have smaller components, but then the losses are so much higher that it still doesn't work out. And there's other materials that have lower losses, but then the components are huge, so it still doesn't work out. And so silicon nitride is precisely at that sweet spot, and that's what we realized in 2018, and that's why we said, okay, we really have to do something with this. So that's a little bit about like why we were able to go fast.
And now, it was that initial machine, right? That one that you borrowed, you essentially improved upon.
Well, I mean, that's maybe not. Okay, I think if you say it like that, that's maybe not doing enough credit to our engineers, because by now there is a lot more cleverness in this device than there was, in the original academic one. But what's maybe also worth saying is the metrics for these kinds of devices are the number of optical channels that you have, and then the end-to-end losses. So those are more or less the two things that you care about. And what we were able to achieve, because we had this very good underlying technology, we were able to achieve what was at the time the largest processor in the world with 12 channels. And we also call these channels Qmodes. That's something that we can go into later. And then with also the lowest losses in the world, right? So eventually and then we put that out there in a webinar So if you go onto our YouTube channel, you can look up the webinar from 2020 where we present this 12-mode processor, and then actually earlier this year we improved on that further and we put out a 20-mode processor. And that processor has about 2.9 dB of optical loss. So that's about 50% of optical transmission if you don't speak photonics engineer. And so it has 20 channels, and this is, as I said, this is the largest number of channels reported in the scientific literature. So this is something that we're very proud of.
That's exactly what I was going to ask you about next, the newest one having 20 Qmodes. Did you want to just take a step back and explain to listeners the difference between Qmodes and qubits?
Yeah, so a Qmode is essentially for linear optics the analogon of a qubit, right? And so linear optics is a restricted model of quantum computation where you do not have access to all of the operations that you have access to in a gate-based model, but where, of course, you have the big advantage that linear optics is a relatively straightforward thing to implement in an experiment. So if you are aware of the recent quantum advantage demonstrations that have happened at the USDC in Shanghai in China, then this is also linear optics, right? So it's those kinds of models it's that kind of model of computation that this QuiX quantum photonic processor ultimately slots into.
And the biggest criticism of that Chinese experiment was that it wasn't solving a real problem, which I guess is a theme that comes up in quantum advantage experimentation. What types of problems can you apply your processor to?
Well, let me say something first about the point of quantum advantage experiments not solving a real problem. Because I feel that there has been a little bit of moving of the goalposts by some people in the community. So, after this, and this is not something that's even specific to optics, right? So after this, after the 2019 Google quantum advantage paper came out, there was similar criticism where people said, but this doesn't actually do anything useful. And I think the counter criticism to that is very simple. It's just to say, well, no one ever claimed that it did, right? And so it's in that sense, I don't agree with the people who have redefined the word quantum advantage to mean useful quantum computation, because this is simply, quantum advantage has a very clear-cut, computational complexity definition, and I don't see why we should be modeling with that, let's say. Of course, obviously, once you have achieved this, the next question is, okay, what is it good for, right? And so it turns out, the question of, so I'm a hardware guy, right? Like I ultimately make quantum photonic hardware. And so I would say that the question of what you can do with linear optics has not nearly received the amount of attention from theorists and from computer scientists that it should have received, but there are good ideas out there. So it, for example, turns out that these kind of linear optical systems map onto the structure of graphs. So there are certain problems of finding, it goes maybe a little bit too far to discuss exactly how this works, but there are certain problems within graphs where you can find, where you're looking for certain structures in these graphs, or you're looking to identify whether a graph has a particular hidden structure, where you could do this with such a device and you could not do it with a classical device. And this maybe sounds a little bit abstract, but if you consider that you can represent